Mute. Welcome back. So I wanted to update you on the fact that I finally redid the slides with white fonts there, because that was hard to read. And normally it's also uploaded there. So if you re-download it everywhere now, you should, who sees more clearly now? Most of you, okay, very good. So I did it everywhere. There was a dark background I changed to have more contrast. And the same goes, you know, here in these tables there. So now you see better if you have duplicate values and so on. Okay. The theorems, the super keys, the wow, we already did a lot. Okay. So this is where we were. We know what a functional dependency is. We know what a super key is. We know that a candidate key is a minimal super key. Now I have a question for you. Can we have several candidate keys on a specific table or a specific universe? So if I give you plenty of super keys, I give you all the super keys, can we have several candidate keys? Yes? Why? Maybe the microphone so that people on Zoom hear.
So it's hardly difficult. So if there is two types of primary key with one attribute for each one, then both of them needs a candidate key.
Yep, that is correct. Correct. So you could imagine, for example, let's take a relational table with two columns, and all the values in the first column are distinct, and all the values in the second column are also distinct. Does everybody agree that if you have at least two records, then the first column alone is a candidate key, and the second column alone is also a candidate key? Who agrees with that? Right? If the values are without duplicates. Okay. Okay. So now here's the thing, because you might think minimal, that sounds like there can only be one, right? But the two letters A and L are important. I didn't say minimum, I said minimal. Do we have mathematicians here? No mathematicians in the room? Okay, well, I'll be the mathematician. So what's the difference between minimum and minimal? Minimum is something you have when you have a relationship that is called a total order. For example, if you have numbers and I give you any two real numbers, you can always compare them. Right? If they are not the same number, then there's always one that is smaller and one that is larger, always. So now if I give you a set of numbers, of real numbers, I'm careful if I go into quaternions or complex numbers, you might argue otherwise, so real numbers, I give you a set of real numbers and I ask, how many minimal numbers are there? Only one, right? There's only going to be ever one single minimal one. And in fact, it's called a minimum. But the reason why there's only one is that you can always compare two numbers. Why is that not the case here? Why can I not say minimum super key? There would be only one. I cannot say that because this, I told you it's about inclusion on sets. We are comparing for inclusion. A set is smaller if it is included strictly in the other one. But inclusion is not a total order. If I give you two sets, maybe, let's call them A and B. Maybe A is included in B. Maybe B is included in A, but maybe neither. Maybe neither. Maybe A and B intersect, but also have elements that the other don't have, right? In that case, it's not the case that either is included in the other. This is why here we cannot say minimum, right? If you have a relationship that's not a total order, it's only a partial order, then you can have several minimal AL at the end, minimal elements. For whom is that clear? Okay, very good. So this is why you can have several candidate keys and there doesn't have to be just one. But then that's a problem because the whole point of doing all of that with the functional dependencies, the super key, the candidate key, and so on, is that we are trying to find a primary key here. We are the database designer and we're asking, okay, what should we pick as the primary key? So in the beautiful world in which there would have been a minimum super key and just one, then that's easy, that's the primary key. But what's going to happen a lot is that we might have several candidate keys. And in fact, that's why it's called candidate key, because these are candidates. And who is the jury who decides which one of these candidates keys is the primary key? Well, that's you. That's the database designer. It's a human decision. You're there, you look, okay, what makes sense? This makes sense. Okay, here's among these candidate keys, I'm picking this one that is my primary key. And the primary key is just a candidate key, one of them selected by a human being who is the database designer. That's a primary key. So this is why when you asked earlier, is a primary key a super key? Yes, by definition, because a primary key is one of the candidate key and a candidate key is a minimal super key. Ergo, a primary key is a super key, always. Okay. For whom is that easy, what I just said, right? That should be intuitive, right? Okay, I see heads nodding, so I'm assuming that's okay. I have a few more slides just to animate. So here's a relational table. 3 columns, ABC, 3 records, 3 rows. Okay, now let me ask easy question. Is A a super key? The column A. I see plenty of heads doing no, and yes, indeed. Why? Because we have the value A, small a, that is several times here. So if I give you the value in column A, that's not enough. Okay. B is not either, because here you can see that's the value C is twice, so that's not enough. And C is also not a super key because you have 1 and 1, so again, that's not enough. Now, A and B together are a super key, right? Who sees that? Okay, very good. Because you see that if you take jointly the value of A and B, then you don't have duplicates anymore. You have AB, you have AC, you have BC. So that's enough to identify the whole tuple. Just look for duplicates. Okay. Now, who sees that BC is also a super key? Okay. Who sees that AC is also a super key? I did it on purpose. I promise. That's exactly how I filled the table. I had this intent. And who sees that ABC is trivially a super key? Here, there's no thinking needed, right? Since AB is a super key, you can add as much as you want. You can add C, it's still a super key. Okay, very good. Now, I know A is not a super key, B is not a super key, C is not a super key, AB is a super key, BC is a super key, AC is a super key, ABC is a super key. What are my candidate keys? Yes, over there. Microphone.
The first 3, so
Yep.
AB, BC, and AC.
Exactly. These are minimal super keys. ABC is not minimal because you can remove A or B or C and it's still a super key. And AB is minimal because if you remove A or B, then you have A alone or B alone, right? And we also already saw it's not a super key. So this is why, yes, indeed. So here we have 3 candidate keys, 3 of them. That's an example where we don't have a single minimum super key. Okay. Now, let's look at that table. I was a bit careful. I placed the values in there in such a way that I trigger the right functional dependencies there. But basically here, product alone is a super key, right? How do I see it? It's only non-duplicate values in there. So if I know the value of product, then I know the tuple. Okay. This is a super key that's trivial. If I take a super key and add more, it's still a super key, right? So here it's trivial that if I add more, it's still a super key. It's trivial, trivial, trivial. Who understands it's trivial? Right? If I augment or add to a super key, it's still a super key. Okay. This is not a super key. I'm repeating myself. We already saw it before. Here, why is it not a super key? Well, for 2 reasons. Because 800 repeats and 300 repeats, right? So this is not a super key. This is also not a super key. Well, it's not trivial here because I can add to a super key and it's still a super key. But if I add to a non-super key, it could become a super key, right? So here it's not trivial. How do I know it's not a super key? Well, let's look for duplicates. You see that the duplicates is 300 high-tech. 300 high-tech appears twice. This is why it's not a super key. If I tell you 300 high-tech, you don't know which one of the 2 tuples it is. This could be a super key, but no, it's not either, because again, I was very careful when I placed the numbers in there, that 300 high-tech 4 is also appearing twice. So that's still not enough to know the price, the category, and the stock in order to identify the tuple. Okay, that's not a super key. This is also not a super key because high-tech repeats even 4 times and entertainment repeat twice, still not a super key. This could have been, but no, it's still not a super key because now we have high-tech 2 that repeats, high-tech 4 that repeats twice. So this is not a super key. And this is not a super key either. Well, if you take a subset of a non-super key, it's still a non-super key. It's just the converse of the superset of a super key. Okay. And not a super key. Why? What do I mean here? Well, I mean the empty set, right? Because I didn't color anything. So the empty set is also not a super key. This is true as soon as you have at least 2 records. If you have 2 records or more, then the empty set is not a super key because you can not tell the tuples apart. Okay. Now, this here is a candidate key. Why? I need to check 2 boxes in terms of paperwork. First, I need to prove it's a super key. We already have here. We already said it's a super key. And why is it a candidate key? Because it's minimal. Because what happens if I remove products to a set that only contain products? Well, that's the empty set, and the empty set is not a super key. So I have proven that product is a candidate key. Okay, for whom is that clear? Okay, and probably that's going to be my primary key too, right? Because that actually kind of is the natural thing to do. Okay. This is a super key because if I add more, it's still a super key. It's not a candidate key. Why? Because if I remove price, it's still a super key, right? So this is not a candidate key and so on. And I could say the same of any superset of a candidate key. Any strict superset of a candidate key is no longer a candidate key. Okay. Now I have a few theorems for you again. I love throwing them at you for you to think offline. So theorem 1 says, a relational table always has at least 1 candidate key. It cannot be that there's none at all. This, in order to see that, is that if you keep removing attributes, then you end up with the empty set, right? So in the worst case, the empty set would be your candidate key. So you will never have no candidate key at all. I think it's true. Oh, actually, I'm not sure. It might not be true for infinite sets. I was like asking, is there always a minimal element? But I think you might still find some pathological cases with infinite sets where you might not have any minimal one if you have an open lower bound. For whom is that actually making sense? Has nothing to do with databases, but okay, some people are math savvy. Okay, it doesn't matter what I just said. I was just, doing math. Okay, so a relational table always has at least 1 candidate key. Theorem 2 says, if I have an empty relational table, meaning no records at all, then the only candidate key is the empty set. Who sees that? Right, it's the empty set. Because how do I prove that? Well, first, the empty set would be a super key, right? If I have a relational table with 0 or 1 records, we've already established that the empty set is a super key. So all I need to prove is that it's minimal, but this is trivial. The empty set is always minimal. You can never remove anything from an empty set. So that's the reason why it's a candidate key. And the only one, it's because it's a subset of anything else. So if the empty set is a super key, then nothing else can ever be a candidate key. Okay, so you see, it's just cognitive gymnastics to think about these things. You can draw to convince yourself. Theorem 3, if a relational table has exactly one row, then the only candidate key is the empty set. That's kind of a repetition of the partial reasoning of before, is that if there's 1 row, the empty set is a super key. Why? Because you know the tuple, there's only 1. So you don't need any information to be able to say that this is the tuple. So the empty set is a super key. It is a candidate key because it's minimal. You cannot remove anything anyway. And it's the only one because it's a strict subset of anything else. So you cannot have anything else that would be a candidate key. And theorem 4, if a relational table has exactly 1 attribute and at least 2 rows, so we are talking about just 1 columns, but at least 2 records, then this 1 column, the singleton set with just 1 column, is going to be the only candidate key. Again, whenever I say the only candidate key, you need to prove 3 things. First, it's a super key. Second, it's a minimal super key. And third, it's the only one, right? So in that case, it's a super key because set semantics, all values have to be unique because there's only 1 column, so it's a super key. It's a candidate key because it's minimal because you cannot remove any attributes, and that's because you have 2 rows that you cannot remove any attributes. If you have at least 2 rows, if you remove an attribute, it's the empty set, but the empty set is not a super key if you have at least 2 rows. And the only one why, well, the other one would be the empty set, but the empty set is not a candidate key. So the only one you have is attributes. Okay. So I know that now I just move my hands in all directions talking about these theorems. It might be a lot to digest, but just think about it offline, right? Just draw concrete examples of tables that are empty, 1 attribute, 1 column, 1 row, 2 rows, and so on, and try to figure it out, right? Who now has an intuition for candidate key? Okay, so if I give you a table and I tell you there's nothing accidental, who can tell me the functional dependencies, the super keys, and the candidate keys of a concrete example? Okay, most of you, very good. This is exactly what I wanted to achieve. Okay. Now I'm just repeating what I said, that you as the database designer are free to choose among the candidate keys which one you want to select as the primary key. Here's an example. Here we have a table with a customer ID, a first name, a last name. So these are people in there, famous ones. And we are looking for the super keys, the candidate keys, and so on. Okay, so let's try. Well, in order to do that, we need to think in general, right? We need to think that there might be accidental dependencies in there. But I did change a bit the names in order to make sure that it doesn't happen too much. But let's see. So if you actually do your analysis with the schema in mind, now the universe of tables, what you're going to find out is that the customer ID is a super key, right? So let me show you how I interpret this. So here, what I drew in colors there, these are basically sets of attributes. So here it's all the 3, 2 of them, 1 of them, 2 of them, 2 of them, 1 of them, 1 of them. Okay. So customer ID, sorry, no, here it's alone. Customer ID is a super key. Who agrees? Right? It's just because it's an ID. Whenever I call something an ID for identifier, it's the intent that it's actually a primary key, right? So customer ID is going to be in particular a super key. Then you can deduct that any superset of that is also a super key, right? Customer ID first name, last name is also a super key, customer ID first name, and so on. Now you could argue that if you're small enough, first name and last name together might be a super key, if you're lucky, and you don't have 2 people with the same complete name, right? The first name alone, probably not a super key, right? First name alone, no. There's plenty of people with the same first name, and the same for the last name. People in the same family have the same last name. So this is why I put like here, not unique, right? These are not super keys. Okay. Now, this here, the 3 together are not minimal. Customer ID first name is not minimal. Customer ID last name is not minimal, because customer ID is the minimal one, right? So customer ID is a candidate key, and first name together with last name is also a candidate key. Okay, so these are the 2 that we are going to keep, right? We have 2 candidate keys, the customer ID that identifies the whole tuple, and the first name and last name that identifies the whole tuple. Which one do you pick as the primary key? Yes, maybe the.
The customer ID.
Yes, that's probably wiser. I totally agree. And that's here exactly the reasoning that technically, if you analyze data that is small enough, there's no collisions. But if you think about the future, it's very likely that first name and last name together would only be a super key by accident, right? So I did it, for example, I did it on purpose here that there's 2 people called Euler, last name and so on. And did I put, yes, I also put twice the same first name here. But what happens in that table is that the super key first name, last name is accidental. It's an accident. So customer ID is really the primary key you want to pick. Is there a question on the chat?
Oh, how's first name, last name a candidate key since it is not minimal?
It is minimal. Why is it minimal? Because look, first name is not a super key. Ada. So first name is not a super key. Last name is also not a super key. Euler, right? So it's not a super key. So this alone proves that first name, last name is minimal. Sorry, I should not make that mistake. I explain the difference. if you take first name, last name together, you cannot remove first name because last name is not a super key. And you can also not remove last name because first name is also not a super key. So this is why first name, last name is minimal on that example. Do you see it? Just checking, person who asked. Yeah. Both together, exactly. A super key is always a set of attributes jointly. So it's first name, last name together that are a super key. And it's minimal because you cannot remove anything. And the point I'm making there is that when you select the one you want, you probably do not want to consider that first name, last name is going to be a super key forever. Because if you have millions of people, it's almost guaranteed that you're going to have people with the same names, right? So first and last name. So this is why customer ID is going to be the primary key. In fact, it's a very common design. Almost when you do professional databases, professional websites and so on, you're almost always going to have some ID that is your primary key of your table, right? Customer ID, product ID, and very often you're going to say not customer ID, but CID, product ID, PID. So whenever you see these three letters, like whatever ID, this is very likely the intent that it's the primary key. You might also have tables that have several ID columns that together are a primary key, but these are tables meant for joining. These are tables meant as relationships between, for example, products and customers. Okay. Okay. Now, formally, this is basically the sort of analysis we can do in a table. We can list the super keys. So I wrote them down here, customer ID, first name, last name, blah, blah, blah. The candidate key is customer ID, first name, last name. And the primary key, we're going to pick customer ID. What you see in a lot of database textbooks is the notation at the bottom of the screen. So basically what you're going to see is the name of the relation right here. That's somewhere R here. You can also write just R. So here I put attributes. And here, this is the schema. So basically you have customer ID, first name, last name. These are the attributes. And you underline the primary key. More precisely, you underline each attribute in the primary key because the primary key could have multiple attributes. Okay, for whom is that clear? So this is a very common notation. You might see it in exercises or the exam that we give you a list of attributes and we underline the ones that are part of the chosen primary key. Okay, who is with me? Okay, now we are going to continue. Also to something trickier, keep increasing the difficulty. It's actually super interesting, but we are going to explore that. So no questions? Have a chance to ask a question of something we've done so far, everything we've done so far? Yes, we have a question over there.
Yeah, a question on the choice of the primary key. So let's assume customer ID and the first and last names are both
Super keys.
Super keys and candidate keys.
Yeah.
Is there an advantage of selecting one attribute only on a computationally?
Computationally, is that a criterion? I think you could make an argument about that it could be simpler to actually, look up an index. If you build an index, it's easier to, because we'll see indices in a few weeks, right? And the intent is that you're going to index on the primary key in order to retrieve the tuples very quickly. So I'm tempted to say yes or yes, kind of. But what I would like to add probably is that the motivation for the primary key is very often going to be a real life thing. It's going to really be a call by a human being, that the primary key must be meaningful in terms of, what you're doing. It's like object-oriented programming. Your database is a model of the world. It's some mirror of the real world. So what you have in the tables must make sense, right? It must reflect your view of the world or what you are saving in your database. So I think that while it is true that you probably want to design the primary keys to be as small as possible, you still want for it to make sense. Now, if you come back to this choice of customer ID, you could argue that part of the reason why it's very common to artificially create an ID column with unique values, for example, integers, and call it an ID and make it a primary key, you could argue that the justification is what you say, that computationally having a single column is easier to handle. There is probably a little bit of truth in that as well, right? Yeah. You noticed everywhere, in fact, the IDs, they are not only the database, we all receive bills, right, that we need to pay. And in the bills, there's always a reference, some ID of the bill, and that's probably what they also have in the database behind, right? So you see IDs everywhere. The social security number of the tax return is also an example of probably the ID they have. It's very likely the tax office has a relational database, right? It's very likely that your social security number is the primary key where they store the taxpayers. Okay, did I answer your question? Okay, awesome. Okay, no more questions, last call? Okay, so let's move on then. Let's move on to something even fancier. Now, I'm going back to functional dependencies, but now let's consider several of them. Let's imagine we have a universe of tables, and we're considering the functional dependencies that are applicable to that universe of table, meaning that all of the tables in that universe fulfill these functional dependencies. Now I'm going to use lowercase to disambiguate a bit because I use the uppercase for the sets of attributes, right? And now I'm going to use the lowercase for the attributes themselves, right? So for example, if you see AB functionally determines C, AB is a set of the two attributes A and B. We drop the curly braces, and we are going to even drop the commas in a bit. It's just for convenience, right? Theoretically, we should put the curly braces for the set and the commas to separate them, but you'll see that the notation is going to become a bit more lightweight. So here we have that the columns A and B together functionally determine C. The columns A and B together functionally determine C, D, and E, and the column A alone functionally determines columns D, E, and column F. Okay, so this is an example of what we could have. We have a universe of tables, and we have these three functional dependencies. So given that, we can do actually super cool things. And the first super cool thing we're going to do is computing the closure of a set of attributes, given a set of functional dependencies like that. You will see it's actually fun to do. So here we have a set of attributes, A, B, C, D, E, F. That's the set that I want to compute the closure of. And I have, as I said, some set of functional dependencies that are applicable to my universe. So you basically get that set while you design your schema. This is what we've been doing this and the past week, right? So this is where it comes from. But we have a set of functional dependencies. And I'm going to assume that I wrote my functional dependencies with single right-hand sides, meaning that I only have one column on the right every time. I can always do it by splitting them. I'll come back to it later. So now here's what's going on. I have a functional dependency here in my example that A and B together, column A, column B together, functionally determine column G. And I have my attributes A, B, C, D, E, F. Think of it as what I know. I know A, I know B, I know C, I know D, I know E, and I know F. I want to know everything I know. So I look for a functional dependency, FD, such that the left-hand side is included in my set of attributes. So I know A, B, C, D, E, F, so I know A and B, right? So on the left, I have A and B, and I know them. They are in the set over there. But the right-hand side is not. I don't know G, or at least I didn't know that I knew G, right? So let me repeat. What's going on here is that we know that knowing A and B, you know G. That's my functional dependency. And I also know that I know A, B, C, D, E, F. What can I infer? Let me reformulate. I know A, B, C, D, E, F. And I also have the information that if I know A and B, then I know G. What can I infer from that? Yes, exactly, that I know G. In other words, we can add G here. So what's going to happen is that I'm using that knowledge from the functional dependency that if I know A and B, then I know G, in order to expand my set of what I know. So if I know A, B, C, D, E, F, then I know A, B, C, D, E, F, G, right? And that came from the functional dependency, right? Again, what happened is that the left-hand side, what's on the left of the arrow, was in my set, and what's on the right was not, okay? So that's what you do to compute a closure. You basically keep doing that all over and 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 all over again until you run out of functional dependencies and you cannot add anything, right? Okay, so in that case, let's assume we manage to add H and I on some different example here. Then we see that we note with a plus here that this is the closure of A, B, C, D, E, F, right? So this little plus is just a notation for that. Okay, and that could happen, for example, if we found that there is a new functional dependency. Here I was mean, I didn't split it with single right-hand sides, but I'll come back to that later. So basically I had the information that if I know A, B, C, D, E, F, then I know G, H, E. Okay. Oh, I see, I know what I wanted to say here. I was like, what is even that slide? This is what I wanted to say. Imagine that we started with A, B, C, D, E, F, and we managed with some set there to expand it to G, H, I as the closure. Then what we can claim is that we've discovered a new functional dependency, which is everything in there functionally determines everything in the closure. So we can add to the toolbox this as a new functional dependency. This is what I wanted to say. Okay, who is following? Okay, I'm gonna increase the number of raised hands with an example. There's nothing better than a concrete example, so we'll do it together. We are going to consider this set of functional dependencies. I'm starting with A and B, so I know A and B, and I'm asking what else do I know than A and B, right? So what is the closure of A and B? So look, first I'm splitting stuff here. You see, AB functionally determines C and D. I'm just splitting it. So if A and B give you C and D, then A and B give you C and A and B give you D, right? It's trivial. I'm just splitting here and I'm splitting here. For whom does that make sense? If I know C and D, then I know C and then I know D. That's simple as that. So now I have only one single letters there. It's just a matter of convention, but you know, we're in Switzerland, we like to tidy things and make everything orderly. So in order to make things orderly in there, we just split so that we have right-hand sides that only have one attribute. Okay. And now we just iterate. Okay. So we initialize. Okay. So AB give us AB, functional determines AB. So we look for a relevant functional dependency. Oh, I found one here. A functionally determines C. So if I know A and B, I know C. There you go. So I add C there, thanks to this one. And now I iterate. So now I put it in gray. So I gray it out because I used it. And I continue. Okay. Now here's an interesting one too. If I know A and B, then I know D. So if I conclude here, I can add D as well, because A and B I have A and B already. Okay, so I know D. There you go. Here's another one. If I know A and D, then I also know E. Well, I do have A and D already because indirectly, right? I know A, B, C, and D. So A and D I know, and thus I can add E. Who sees that? Okay. So I'm adding E as well. There you go. Okay. Here's another one. If I know A, B, and C, then I know I. But I did have A, B, and C already, so I can add I as well. Okay. I just keep iterating and iterating and iterating. If I know I, then I know J, so I can add J as well. If I know I also know K, so I add K. If I know C and J, I know L. Well, I did have C and J already, right? So I can add L. There you go. And we are done. I think there's nothing else we can do. So you see, we've established that the closure of A and B is A, B, C, D, E, I, J, K, L. What it means in everyday world is if I know A and B, then I know A, B, C, D, E, I, J, K, and L. Right. Who followed? Who can compute the closure of any set of attributes? Okay. So you'll have exercises probably on that. Okay. Well, it turns out there's actually quicker ways. I mean, you can do it brute force, of course, like that. But it turns out that there's a whole theory with rules and axioms and so on that actually can allow you to manipulate them. And this is what we are going to now. We actually have rules. They are very intuitive. There's going to be some fancy formulas in there, but every time there is an intuition with what's going on. And it's the intuition you need to focus on. So I have a transitivity rule. It looks complex, it's simple. Here it goes. Imagine that I have a rule that says, if I know A, then I know B. Right? So if I know A, I know B, and if I know B, I know C. So what can I conclude? If I know A, then I know C. Exactly. So this is exactly what this is saying. That's a transitivity rule. I can, by transitivity, say that if I have A functionally determines B and B functionally determines C, then A functionally determines C. Okay. Okay. So graphically, what's happening is that I can graphically put it like that, visually, that if I had a set of functional dependencies where I had A gives me B and B gives me C, then I can conclude that A gives me C, right? This is just a visual for that. I can also add, I can expand, I can also keep A gives me B and B gives me C and add A gives me C, right? I can also keep the old ones. Okay. Now, if I use this rule, it's a rule of implication, right? If I have what's on the left and I have what's on the right, I can also talk about equivalent sets of functional dependencies, right? If they are following from each other. Okay, here's another rule. It's called the splitting rule. Here it goes. I already used it actually. Imagine that I know that if I know A, then I know B and C. Do you see that it implies that if I know A, I know B, and if I know A, I know C? Who sees that, right? It's just saying it in everyday world is usually enough. So it's just that we can split, right? I can split that rule on the left, A functionally determines B and C, into A functionally determines B and A functionally determines C. Okay. It goes the other way around. Turns out it goes both ways. If I know that A functionally determines B and A functionally determines C, then I can infer that A functionally determines B and C. In other words, with everyday words, if I know A, I know B, and if I know A, I know C, I can infer from that if I know A, then I know B and C. Okay, is that clear? Okay, so visually, this is what we've established. We have two equivalent ways of saying things. Either I can say A gives me B and A gives me C, or I can say A gives me B and C. It actually doesn't matter. It's a matter of convention, actually. There are people who like to split everything and use the convention on the left. There are other people who prefer to compact things a little bit, and they prefer to group everything together with larger right-hand sides. You will see in real life both conventions. I tend on my slides to use the left one, so I split everything into a singleton right-hand side, but you might see in books or in the exercises the other convention. So just do not be surprised, it's just equivalence. Okay, here's another one, reflexivity rule. Imagine that I have a set of attributes that is a subset of another. So A is a subset of B. Do you see that if I know everything in B, then I also know everything in A? It's because it's a subset. If I know that it's raining and that it's cloudy, then I also know it's raining, right? It's just that I can take something smaller and I know it as well, right? So if A is a subset of B, then B functionally determines A. This is almost trivial, right? But it's still an axiom that we have. Okay. So it means that I can make relational functional dependencies pop up out of nowhere, right? So on the left, it's like the quantum void, right? So on the left, I have absolutely nothing. And just like that, out of nowhere, I can say that ABC functionally determines A and C. It's just always true, trivially true. Who agrees? Okay. So if I know A, B, and C, then I also know A and C. Okay. Here's another one. It's an augmentation rule. It says that if A gives me B, then A and C give me B and C. I just add the same thing on both sides. If I put it in everyday words, if I know that I know A, thus I know B, then if I know A and C, Then I know B because I knew A, but I also know C because I added it on the left too. Okay, this is called the augmentation rule. Okay, these are plenty of actions, right? I showed you, so how many of them? We had the transitivity rule, we have the splitting rule, we have the combining rule, we have the reflexivity rule, we have the augmentation rule. That's a lot of them. Well, there are people who tried to, whenever you have actions like that, they try to find the minimal things that you need. In that case, somebody called Armstrong figured out that it's enough to have just reflexivity, augmentation, and transitivity. These three are enough. The others, they follow. So all you need is these three: reflexivity, augmentation, and transitivity. And they are on the slides before. That's all we need to derive functional dependencies. So it means that you don't need to do things by hand every time. You can just use these rules in order to rewrite your sets of functional dependencies in equivalent ways, right? And I wrote them again, that reflexivity means that you always functionally determine a subset of yourself. Augmentation means you add on both sides the same thing. I put the union explicitly here, but could also be a comma. And transitivity here, that if knowing A, I know B, and knowing B, I know C, then knowing A, I know C. Okay. Okay. That's it for today. I'm going to end things here. It's very fancy, very formal, and so on. That was a lot that I threw at you. Today, I'm still going to verify that you followed, just quickly making sure it's ready. Right. But you see, you survived all this formalism that I threw at you, pretty heavy math. So the best way now is to draw visuals, to try it on real tables, try to figure out the functional dependencies, the super keys, the candidate keys, pick one primary key. And then think of these rules, right? Transitivity, reflexivity, combining, splitting, and augmentation, the 5. Oh, we still have, wow, you did well. You still have a majority above 80. That's excellent. A fragile majority. Aha. Now, of course, it's a quantum system, right? As I measure it, then the system is modifying itself. Okay, we still have a tie. Okay. You did well. Okay. So this was really one of the toughest part of the entire course. So congratulations on having made it. I'm going to continue next week with these functional dependencies, and then we'll move over to normal forms, which is something you should use to create your schemas. Thank you very much for being here. Thank you, Nobi, for being here as well as the moderator. And I'll see you, so enjoy the exercises, and I'll see you next week at the same time at 10 for the continuation of the lecture. Thank you very much.